morning to everyone once again, and welcome to our third of four webinar. I present myself briefly, as most of you already heard my first presentation. My name is Angelo Manfredi, and I am a researcher and a project manager working for Engineering Informatica in Naples, Italy. Previously, I worked more than 10 years in the same company as a project manager for Italian and foreign telecom sectors. Since 2016, I have been in research and development area, and since 2017 as a project coordinator for the European project, the Hyper360. Hyper360 main result is an end-to-end toolset that allows to realize interactive 360 video by adding interactive element to the 360 background video. Our consortium is composed by 8 organizations from 5 countries. The project received funded by the European Union in 2017 and started in October of the same year to last 36 months. Today, we are in the last month of the project. Let's start talking about the project pipeline. Hyper360 project final result is a toolkit that enables the integrated production and delivery of immersive interactive videos. An interactive video is a video where the viewers can not only look in any direction, but also they can trigger interactive elements, for instance, audio, video, HTML panel, to get additional information or to jump to related interactive video. Capture, post-production, and delivery are the 3 main phases of the Hyper360 pipeline. The pipeline is realized by using our suite of software tools. These tools are integrated and can produce and deliver interactive video to play on standard web browser, smartphone, for example, iOS and Android, and web head-mounted display, for example, Oculus Go. The first phase is capturing phase. The tool for capturing can improve the capture high-quality video content and allows the recording 3D performance of virtual character. The project released 2 tools, an high-quality video content capture tool named OmniConnect, and a software tool, Captions, to record 3D performance of virtual character. We call them Mentor, to be later fused in 360 interactive video. The next phase is post-production. Hyper360 project realized the OmniConnect Web tool that allows the adding of interactive elements to a background 360 video file in post-production. All interactive elements will be overlaid to the background video on the fly during the playback. Finally, we have the delivery phase. Hyper360 delivery is a cloud-based. As the content is streamed to lightweight players, it requires network connection. Currently, the content cannot be packaged to be downloaded for offline fruition. In this phase, we realized OmniPlay. OmniPlay is an Hyper360 set of players for interactive 360 video playback that support all Hyper360 features on all main devices, standard web browser for PC, iOS and Android smartphone, and head-mounted displays. Also, we released OmniCloud. OmniCloud is a Hyper360 internal support cloud service that delivers the interactive video realized with the OmniConnect Web and hosts Hyper360 profiling and recommendation engine. Now I will present to you the OmniConnect Web that was realized in post-production phase. OmniConnect Web is a browser-based authoring tool to realize 360 interactive video. By using OmniConnect Web, the director can add interactive element on any background 360 video by choosing from a rich set of possible overlay objects. Before presenting the user interface, let me say that our tool uses a reliable software stack, HTML5, WebGL, Node.js, and MongoDB to manage hotspot data. Moreover, to improve performance and obtain a smooth playback, video content is streamed by a streaming server, video server. Currently, we are using AWS Amazon Streaming Server. Now, let's start with the user interface overview. The interface runs on any browser HTML5 and WebGL compliant. The user interface presents a central video preview area, this one, and two vertical panels on the left and on the right side of the central preview area. The left panel shows all possible hotspots grouped by type that can be used to enrich the background 360 video. All hotspots can be placed in the preview area by clicking the respective type in the panel and then clicking again in the desired position in the background video. The user can later change this position by directly dragging the hotspot marker. The right panel manages the hotspot. It uses two tabs, props and events. The props tabs allow the user to set properties like size, position, and so on for a selected hotspot. By clicking on the events tab instead, the director can access the event management sections that allow him to define the events that all players will interact and react to. The director can choose the events from a pre-configured list, such as on click, on appear, on disappear, and then he can choose which action each event will trigger. For example, open a 2D video, open hyperlink, play another 360 interactive video. This is a 2D video overlaid on the background video file. A video preview will be displayed after a short waiting time needed to load the video. This is another example. This is an image hotspot overlaid on the 360 video file. The image preview is displayed almost immediately. This is another example of image hotspot overlaid on the 360 video file. Above the preview video area, there is a set of buttons to close the current configuration, save the work in progress, delete a selected object, choose which device classes the enriched video will be available. For example, web and/or iOS and/or Android and so on. Publish and publish the enriched video. Publishing is the step that makes the enriched video actually available for players for playback. And finally, we have enable or disable a compass reference overlaid to the video. Below the preview area, in the preview button allows to watch in full mode the video preview in a new browser tab. The preview tabs act as a full web player. Further above the central video preview, in an upper ribbon, there is still another set of buttons that can be used to update the user personal profile or to modify personal credentials. The setting button instead allows to preload the interactive elements frequently used. The hotspot type that can be preloaded are images, file audio, and 2D video. Finally, below the central video preview area, there is a ribbon with 3 tabs that will be presented in the next slide. The tab timeline shows a list of rows, one for each hotspot, overlaid to the background video. Each row lists the hotspot type, its main properties, for example, main and name and time, and 3 buttons that can be used respectively to remove the selected object, to get a brief description of it, and finally focus the central video preview area to it. Several buttons on top are also available on top of the list, allowing the editor to select the row by type, name, description, and so on. The tab jumps summarize all jumps events which have been already defined. Each row shows the trigger hotspots, the trigger event, in this case on click, the target 360 interactive video file, an edit icon to select which hotspot intercepts the event. When the editor clicks these icons, the central video preview area moves to the point in the video timeline when the specific hotspot appears for the first time, and focuses the point of view to it to speed up further editing. The last tab, End of Video, lists all available options to manage the video ending actions. We can set stop to stop the 360 video when it ends, loops, restart it when it ends, or jump lets the director define another 360 video to be played as soon as the current one ends. This is the home page shown by the OmniConnect Web after login. The home page shows a list of cards, one for each background video, uploaded of course in the system. When the user places his mouse over a card, 3 clickable icons appear respectively to edit, play, and delete. Video technical details like video resolutions, codec video, and frame per second, and also video size also become visible. Further information like video name, this one, and also video duration, this one, and submission date are instead always visible on each card. To show how to use OmniConnect Web for enriching a background 360 video, I will show you how our friend and colleague RTI annotated their video. They demonstrated in the first webinar. By clicking on the Edit, the director accesses a list showing the enrichment video configuration that are already available and that can be modified. By clicking on the button plus, the director can create a further enrichment video configuration. Each row in this configuration list shows the configuration name, in this case webinar, the consumer name, if filled, will be shown by the player as a video name during the playback. Whether a mentor is present or not, the action allowed for the configuration, edit, modify name, configuration name of course, copy configuration, and delete configuration. Moreover, on top of the configuration list, it is possible to modify or add a new category name or a new topic data used by our recommendation engine to do its job, which is to emphasize some overlay element during the video fruition. We will go in further details about this in our next webinar. Okay, now let's see how is it possible to annotate a background 360 video file. Okay, the left panel lists all the possible hotspots that can be overlaid to the current scene. All hotspots can be placed in the 360 video area by clicking the respective type in the panel and then clicking again in the desired position in the 360 background video. Okay. One place, the hotspot can be moved by dragging and dropping it anywhere in the video. While dragged, the object border became green, as I'm doing now. Of course, as we are working on a 360 video, the director can freely move in the video preview area by simply moving the mouse. I'm moving freely within the video. And I am looking around. Okay, when an hotspot is selected, as I do now, in the right panel are listed the properties and the events. The properties to set for an image hotspot are info, to assign a name and a brief description to the selected object. Positions, to precisely place the object according to the 3 Cartesian coordinates. load the image file to display. In this case, we load the the file GF name. Time, to set the time interval during which the image has to appear. Selecting full time, the image will be displayed for the entire video duration. If the full time option is not selected, it's possible to define the time frame either by filling the field from and to, or by using the slider. The next is size. Size to define the object size, either by using the slider or by manually entering a numeric value. View options. The first one is a show hotspot. Show hotspot. If checked, the image cannot be controlled by another hotspot. This means that no other object can control the appearing of this image as the action to perform when an event is intercepted. The next option is blinking as a toggle button to activate the blinking and its speed modality, for example, medium, fast, slow. The next one is fixed on the screen to display the image in a fixed position that can be chosen by a pre-configured list. For example, horizontal alignment on the left, center, or on the right. Or vertical, for example, middle or down, for example. Or manually acting on the dedicated position arrows when the checkbox is free positioning is selected. If I check this, I get access to the position arrows. Then I can move the image. Okay. Oops. Okay, the next is on background. It's a default option. The image is shown in the current position. When the options on background is selected, a further forced view toggle button became available. If selected during the video playback, the point of view will be moved to have the object in the center of the scene. The last one is tags. Tags allow the director to add strings with similar semantic meaning that will be later processed by the recommendation engine to provide hotspot-specific recommendation. The tab events show the events like on click, on disappear, on appear that can be intercepted. For each, the director can define the action to trigger, like open a new 360 video, make visible an hotspot, and so on. The action can be chosen from a pre-configured list and are, I'll show you, jump, open link, and drive hotspot. Jump is used to jump from the current video to a new one. For this target video, it is possible to define, in addition, not only a specific configuration, but also when the video will start, starting second, of course, and the starting angle of view. The next is open link. It uses to add the link to a web page that has to be displayed. It is possible to choose if to open the web page in a new browser tab or maximize it and embed it in background video. Finally, we have a drive hotspot. It is used to choose which hotspot must be activated. Now I would like to show you how RT have configured an event. By accessing to Event tab, the event, of course, becomes visible. As you can see, the events on click is highlighted in blue. This means that an action was set for these events. In particular, they choose the action jump to select the video file to play back. They choose a GF video 2 with this configuration. Okay, let me show you another video reached by RTI. Okay, in this video, the director added the hotspot image Armani logo that should be this one. The right name is Giorgio Armani logo. Selecting the image and accessing the relative events tab, you can see that the event on click was chosen to trigger the actions drive hotspot to display other images. Okay, they choose to use the action drive hotspot to show the image Armani Fiori logo, Armani Casa, Armani Dolci, and so on. For these triggered images, the event on click was also triggered to open a web page. This means that if I select this image, Armani logo, and access to event tab on click, there is the actions open links, and this is the link to open armanidolci.com. I show you another example about drive hotspot action by selecting the image info point. In fact, in this case, when the image is clicked, a transparent panel with additional information becomes visible. I'll show you in preview mode. Using the preview, you can immediately have a perception about what you are doing with the annotation tool. If I click here, several images appear, then I can click here, and the system opens a link in a new tab. Okay. Okay, perfect. Now I will show you how to configure a 2D video. How to configure a 2D video added to background 360 video. Let me just to say that another way to find the hotspot on the central video preview area is to search them on the timeline. Once found, clicking on the button, for example, focus, the preview area moves to place the selected hotspot in the center of the preview area. For example, if I wanted to search a 2D video, if I click here, okay, the system highlighted the hotspots. Okay, then in addition to standard properties like position and the time and so on, according to the broadcaster need, we also introduced the property cover for the hotspot HTML page and 2D videos. This property allows the director to choose a cover page to overlay the entire area hosting, the 2D video and the HTML page. This cover page, when I click, will activate the 2D video or the HTML page. Then this means that for the 2D video, Armani Gioia, RT has added a cover page, a transparent cover page. The name of this image is Trasp, and set the options full screen. This means that the 2D video will appear in full screen mode. Okay, I will show you the result about this configuration. Now here, if I click, a 2D video appear. Okay, that's all. Thank you so much for your attention. Now I leave the floor to my colleague and friend Antonio Caracottas of CERT-ET for the next presentation.
Hi everyone, we'd also like to welcome you to this webinar. I am Adonis. I am a member of the Visual Computing Club at the Information Technology Institute at the Center for Research and Technology LS in Thessaloniki, Greece. And now we'll talk about volumetric video and 3D asset creation. And specifically, we'll talk about the 3D renderer and how we can create the 3D renderer and some technologies that can assist the producer to embed 3D assets in 360 videos. So this is an overview of the section of the webinar. We'll talk about volumetric video capturing, performance capturing, and 3D asset creation to finally present you, as I said, the set of technologies for compositing animated 3D assets in 360 content. And more specifically, we'll see what volumetric video is and how we can capture volumetric videos, as well as the challenges that these may have. We'll talk about Sheriff's template-based performance capture scheme and how we convert volumetric videos to ready-to-use 3D assets. And finally, we're going to describe AI assisting technologies for composing the 3D content in 360 media. So let's begin by describing what a volumetric video is. So a volumetric video is essentially a 3D video. It is a type of media in which accommodates 3D information and how this information changes with time. There are two basic representations. That is a point cloud, which, as the name states, is a cloud of points in 3D space, and meshes, which are 3D surfaces defined by polygons, usually triangles. And as you can see in the slide, I really believe that you can make the difference. The video on the left is a point cloud volumetric video, and the video on the right is a mesh volumetric video. So on the video on the left, you can clearly see each point in the 3D space. So now that we know what the volumetric videos are, let's talk about how to capture them. There are many different methods in the literature, and over the years, many big but small studios too emerged that give the ability to record performances. But in all of the cases, volumetric video capturing has to do with utilizing a set of different sensors in order to capture 3D information. So these sensors can be simple RGB cameras, like the normal digital that we all know of, or in many cases RGBD cameras with which you can capture color and depth information simultaneously, or infrared cameras too. The methods utilized can be multi-view stereo, or with the recent advent of AI techniques and deep learning, many methods emerge that are based on sparse RGB viewpoints, which means that they labor at very few RGB sensors only. So here in this picture, we can see Microsoft's Panoptic Studio, which is an enormous platform and is composed of 480 VGA cameras, 31 HD cameras, and 10 Kinect sensors. And here we can see again Microsoft's holoportation platform, which comprises 8 camera pods, each one consisting of an RGB camera, 2 infrared sensors, and a structured light depth sensor. And finally, here, this is an AI method which outputs volumetric video from just 4 RGB viewpoints. So let's see how we approach volumetric video capturing and how we at Hyper360 capture volumetric videos of human performances. So in Hyper360, we targeted a low cost compared to current state-of-the-art platforms, portable and easy to use volumetric capturing platform. We built a hardware and software studio based on commodity RGBD sensors. Namely, we employ the recently released Kinect for Azure and Intel's RealSense sensors. And we utilize at least 4 sensors, but we can add more if there's any. So we use a capturing node for each sensor, which basically is a mini PC that controls the sensor. And we use mini PCs because they are easier to move around, but someone could use any other PC that you might want. And the main workstation, which controls the capturing workflow. So these are all connected inside a local area network via network switch with high bandwidth rates because there is a demand for high bandwidth for each device as both RGB and depth data are streamed into the network. So on the video on the right, you can see our volumetric video capturing software platform. You can see its separate view as well as the connected devices on the panel on the top left. And basically me, that's me inside. And I'm going inside the capturing space and you can see the light point cloud in the 3D viewport. So as you can probably imagine, orchestrating and rolling all these sensors in a common ground has many challenges. The main ones are the quality of the sensors. Typically, RGBD sensors are usually noisy, and their quality and performance depends on the state of the surrounding space, such as lighting, sometimes temperature, etc. Another challenge is the temporal synchronization of all these different sensors, meaning that we need each sensor to capture frames at the same time, because we'll see temporal artifacts in the video. That is one view won't be in sync with another one. So for example, in one view a hand can be raised, while in the second it is raised with a delay, and this is really visible and annoying. And finally, one of the most common source of problems in multi-view systems, like the one we described here, is the sensor's external calibration, which means to know the position of each sensor in 3D space. So let's see what we do about all of them. So regarding the quality of the sensor, here in the video, you can see that the outputs are really noisy, and tada, here they are. The result is really more. It's more smooth. So we employ spatial and temporal filters on the depth channel of the sensors to accommodate for the high frequency noise. So you can see that here the movement is much more smooth. And now I disabled them again. So, okay, now here we'll see it again. Okay. So that's how we account for high frequency noise in the depth channels. So regarding the temporal synchronization, we employ a software implementation of a IEEE based protocol. It's a precision time protocol, or PTP, for synchronizing different devices in the network. There's not much more that you can do besides implementations like this. And finally, regarding the sensor calibration, we developed a deep learning method, which utilizes 4 standard packaging boxes from a Swedish company that we all know of. And so you can find them anywhere, and they're pretty cheap. The algorithm tries to find correspondences of the box faces between the different views. So this should be viewable in. So this was a video. So the algorithm finds correspondences between the faces of the boxes for each of the different views. And the fact that this is a deep learning method makes it pretty easy to use, and you can calibrate the system at the click of just one button. So imagine the systems like the ones I showed you before, like the Panoptic Studio, which has, I don't know, 500 sensors. So you have to know the position of all of the sensors in 3D space, and the calibration procedure is really cumbersome and requires much technical knowledge. So on a system like this one, anyone can use it with not that much technical know-how. So finally, the resulting output of the volumetric capturing platform is a set of RGBD video sequences which contain all the temporal spatial information used to capture them. So here we can see some sample frames for 4 views and the color and the depth channel in correspondence with each other. So now that we know what volumetric videos are and how we capture them, let's change the chapter and move forward to tracking human performances and creating 3D assets out of them. So the method we use is a template-based method, meaning that we're creating a template mesh, and we try to fit this mesh to the live data that we captured with the volumetric capturing platform. So to achieve this, the template mesh has to be fit with a skeleton structure, so we can animate it. We can move, you know, the limbs around, and skinning weights, which represent how much a given joint in the skeleton modifies the template mesh point. So our tracking algorithm is a modular derivative-free optimization scheme, which tries to fit the skeleton's joint rotations so that the error between the animated template mesh and the live data is minimal. So I will elaborate on that later. So the overall flow of the application is the following. First, we keep a frame from the sequence we capture, and we create a template mesh. Then this mesh is rigged and skinned, that is, we fit the skeleton and skinning weights on the template mesh. And finally, we move to performance tracking, that is skeleton joint optimization. So let's see the steps one by one. So in order to create our template mesh, we first create a point cloud from the multi-view sequence we captured. And the resulting point cloud must be filtered because we don't need all the points of the point cloud. So for example, here, the points on the floor do not have to do anything with the nature and the performance. So we have these boxes that filter out all the points in the point cloud that are outside of them. We then triangulate the point cloud, and the watertight mesh is a result of this. So we use the Poisson mesh reconstruction algorithm that comes with MeshLab. So MeshLab here is a 3D software application for working with 3D data. And then we do some out-of-the-box steps. So we use a number of polygons or triangles in the mesh. We fix some mesh defects and optimize the mesh for rendering. So this is all technical stuff. They have to do with how the triangles are ordered. So they are not, they're out of the scope of the webinar. And finally, we can skin the mesh. So we use Pinocchio, software for automatically rigging the mesh with skeleton and that skinning weight. So as you can imagine, this procedure is really automatic. There are not many things that you need to know or to do about it. So it's really usable by many people without much technical knowledge. And since we have created our template, we can move to tracking. So tracking means that we track the movement of the character we captured in the RGBD data. And the general concept is an optimization scheme, as I told earlier. So an optimization scheme is that we try to minimize or even maximize, but here we try to minimize the error between two quantities so we can achieve a desired result. So here we animate the template mesh in many semi-random position, and I will elaborate a little on the term semi-random later, and calculate the error between the animated template and the live sequence data in order to fit the skeleton joint position so that the animation of the template matches the pose of the live data. So we use an optimizer. Its name is Noldermith optimizer, which is a derivative-free optimizer that uses a solution, in our terms, joint rotations, depending on some initialization values that the user supplies, and then it chooses values according to the simplexter. So this stuff is really too technical, so I added links here for when the presentations are uploaded on Hyper360 website. So anyone interested, check them out. So here in the video on the right, we can see the optimization panel. So here I am modifying the settings of an optimizer. So specifically, I add the joints to optimize. And right here, you can see some error terms. So are the errors that are to be evaluated between the green mesh and the red mesh. So here, the red mesh is our template mesh, and the green mesh is our live data. And the optimizer tries to fit the red mesh to the green one by semi-randomly moving around joints and moving around the mesh. So finally, they match each other. Okay. So right now we'll see this more clearly. So this is the optimization loop in which we follow a human in the loop concept, meaning that we give the ability to the user to pause the optimization loop at fix errors and mistrack joins. So here I loaded an optimization setting right out of the box, because you can make optimizers, you can make groups of optimizers that target specific joints with different settings and save the settings for later use. The performance capture application has many panels that assist the user. So here you can see error evaluation. So these are error values. So you can debug. We have timings for error evaluation, for 3D visualizations, and many things that are outside of the scope of the seminar. So at some point in time, the whitish orangish mesh, which is our template mesh here, will lose tracking of the head joint. So as you can see again, the optimizer moves around the template mesh to match the green one. So there's a little movement here, but you can see that the white mesh head here started to rotate a little bit on the right, and the optimizer started to lose the tracking. Okay, so now I can pause optimization, open up the pause parameters panel, and rotate the head a little. And resume the optimization again. So you don't even have to be that accurate, because if the template head is really close to the live head, the optimizer will adjust them just right. So finally, we can export an animated mesh of the track performance. So Hyper360 tools can export a proprietary format that we use internally. Or even export an FBX file, which is widely used 3D file format in the 3D modeling industry community, and even in the gaming industry, meaning that one could do many things in many 3D software platforms like Maya, 3D Max, or even game engines like Unity or Unreal Engine, etc. So you can imagine the possibility of having real human performances in virtual scenarios. And the modalities that we export is the mesh's geometry, the skeleton and the skinny weights, because they are needed for animating the mesh, the animation sequence, and static and dynamic textures, which is the color of the mesh. So as we talked about the performance capture, so now we'll talk about the 360 and 3D fusion and some AI technologies that we developed for compositing 3D performances in 360 content. So the main challenges of this are the 3D object placement inside the 2D media, not with the traditional sense. The 360 videos are not 2D with the traditional sense, but they're still 2D. They don't have 3D information for that. And another main challenge is to render, that is to make the 3D object appear so as it's seamless composited inside the environment of the 360 video. So let's see what we did about that. So to enable easier object placement, we developed a 360 depth estimation deep learning network that infers depth from a single RGB image. Here you can see two example input images. Here, and the resulting point cloud, which is the result of our network. So here is our network. So here we see two challenging scenes, scene with a waterfall and an outdoor scene. So outdoor scenes are really challenging in general. And here you can see the result of point clouds in and traversing inside the point clouds in a 3D software platform. There you can see the errors, you can see which points are correct, and however, estimating depth is a nil post problem with scalabilities, which in down-to-earth terms means that although the overall structure of the estimation might be visually correct, its scale could be wrong. For example, all the estimated depth information should be shifted by 8.7 meters, etc. So let's go to the problem of rendering 3D objects seamlessly inside the 2D media. So in order to enable correct rendering according to the environment, we use ray tracing, which I believe many of you know what it is with the recent emergence of ray tracing CPUs. So ray tracing basically simulates how light traverses scenes when it interacts with surface in the scene. In simple terms, let's say that we have light here, and the light ray begins from the light source here, and it reaches the surface. So it will be bounced in another direction according to the normal vector of the surface here, which is this little arrow right here. So having this in mind, we developed a deep learning again method for 360 surface normal estimation, which means given an RGB input image, we estimate all these little arrows on the surface. And here are some examples again with our results for the same scenes. And as we can see that here with the waterfall, we have a lot of ambiguities here, and the result is really fuzzy. However, in this image, which there are structures like cubes and columns here and stuff like that, the output result is really more logical. So, and finally, in a similar manner, we developed a low-frequency illumination estimation network that estimates low-frequency color components of the 360 environment map in order to illuminate the embedded 3D model according to the 360 content. So here we can see 360 image. Here is the illumination that our network estimates. It's a low-frequency illumination. So here we have a lot of light. So here the illumination map is a lot lighter right here, and where pixels are darker, we have darker illumination in the estimation. Here is a 3D model with a specific material. We don't care what the material is exactly, but here we can see another 3D model with the same material as this, illuminated with our predicted illumination map, and we can see clearly that it feels like it's a part of the scene here. And here is another example with the waterfall scene, and here that we have a lot of light, we see a lot of contrast in the illumination right here. So with these technologies are a basic step towards assisting 3D compositing in 2D media. And to reach the end of my presentation, here are some samples of huge 360 videos. I hope that these are visible. And we have some, okay, so we got stuck, okay. And here we have some performance captured animations. We can see that there are many challenges here. They're not all, sunny, there are errors. So specifically here at the beginning of the video, you will see the mentor's arm trembling around. Okay, right here we saw that. Here we'll see that my legs, that's me again. So my legs are doing movements that they're not really physical to do. This is an error of the optimizer. But all the technologies are basically a step to make more robust algorithms and move things forward regarding virtualization of real human performances and composing them in virtual spaces. So that was all from me. Thank you all.